All right, now I've got good news. We're going to show you another way to evaluate these limits today. So if you didn't remember the algebra tricks, this there's another method that you're going to be able to do today to evaluate the limit. Now, the first thing that I want you to realize is if I plug in 0, or excuse me, if I plug in 2, I ended up with 2 squared over uh, 2 squared minus 4, which is 4 minus 4. I get 0 on top. If I plug in 2, I get 0 on bottom. So I end up with what's called an indeterminate form. And we said we don't like that, right? That doesn't help us out. It doesn't give us an answer because we don't know if the numerator is going to 0 and the denominator is going to 0, which one's going to 0 faster, and what's our answer going to be. So there's a couple of ways to do this. The first one is just algebra. What if I take the top part and I factor it? I get x minus 2, x plus 2, and then the bottom stays, but then you notice that on the bottom, you have a common factor of x minus 2, top and bottom. So my new limit is actually just the limit as x goes to 2 of x plus 2. Well, now I can do substitution. Oops. I can plug 2 in, and I can evaluate the limit. I get the answer of 4. All right, so keep that in mind because when we do our new method today, we're going to hopefully get this same answer. But the big thing right here is this 0 over 0. And I do want you to notice how I didn't say this limit equals 0 over 0. I said the top went to 0 and the bottom went to 0. Because if I put an equal sign right here saying this limit was equal to 0 over 0, that's not true. That limit is equal to 4. So you have to be very, very careful with your equal signs today, and it'll all make sense as we learn the new material. Well, now, what about this part? If I put infinity up top, -3 times infinity is just going to give me negative infinity. And then if I do the same with the bottom, I get infinity to the 4th power plus infinity times 2. Well, all of that is just going to give me positive infinity. And now I get a negative infinity over positive infinity. But this answer is not equal to -1. These do not reduce out because I don't know right now, I don't know if the top is growing faster than the bottom or if the bottom's growing faster than the top. But this again is one of those indeterminate forms that I can't determine the limit, but that doesn't tell me that the limit doesn't exist. So what was our little method for solving this one? Well, if you notice, the top doesn't, well, actually you could pull an x out and things could reduce. So you could factor the top and the bottom, but what I want to do is notice this. As x goes to infinity, I can use that idea of end behavior, which means it's the coefficient and the degree of the numerator and denominator that I want to look at. So which one is the highest? We're basically going to say this end behavior model says, let's get rid of this extra stuff because that plus 2x isn't going to do much to the graph when I'm going to the very, very far right. So the end behavior model says we can just rewrite this as -3x over x to the 4th, but then wait a minute, algebra comes into play, and this x will go away, and I'll reduce 1 out here. So my new limit, and you don't have to show all this work, you could have just said, oh, wait a minute, I see what's going to happen here, and I know my answer. But this is what's left over. The x's reduce out, 1 on top, 1 on bottom. And now I can use the equal sign because I'm going to actually substitute in and evaluate this limit. Well, -3 over infinity. Well, if I have something that is a -3 length, which sounds odd, and I divide it into an infinite amount of pieces, that's basically going to 0. So this was the end behavior model, and this was just algebra factoring. Quick review of limits day-to-day that I think you're going to like. Um, so we have two things, and I just want you to know if you're thinking about our textbook right now, we are going to not fully directly teach section 4.1 because all it is the application of the derivative. It's saying you now know how to find the derivative of any function that we're going to ever study. And you know the power rule, the quotient rule, and the chain rule, and the product rule. And you even know implicit differentiation. So you know all your methods. Well, what about applying that information? And this is just making sense of this problem. So I'd like you to write this down, but don't write the whole problem. Just write the equation. And I'm just going to add some context to it. So a population of bees has migrated to a town in the Midwest. Suppose the population of bees in the town at time t, which t is given in weeks, can be modeled by the function. So this is like your original position function, or in this case, instead of p being position, it's population. So part A is a very common question that you're going to be asked. I'd actually like you to take a moment right now and see if you can answer these two questions. Find the initial number of bees in the town, and then part B is how many bees are in the town after 1 week. Okay, this first one is actually, both of these questions aren't even calculus questions. But when we start, and I want to find the initial number of bees in the town, anytime you see the words initial, that's referring to when time is 0. So we're basically just looking for what is the population at week 0. So all I'm doing is plugging 0 in here. Now, you don't really have to show a ton of work if you know what's going on. So I've got 39 times e to the, well, this whole exponent is going to turn into 0. And then they are expecting that you know that e to the 0 is 1. That's the reason why they put this problem on there. So then I get 39 times 1 is 39. And then I just have 1200 divided by 40. You don't need to show any of this work. But if you cross the zeros out, 1200 divided by, or 120 divided by 4 ends up being 30. So now they didn't mention here sorry, I just got a question. We're going to talk about the test at the end of the hour on when you can see the questions you got wrong and how to do a remediation. So we'll talk about that. That's all coming up. Okay. It's usually not good enough just to leave an answer as is. Even though they don't ask us, we should always talk about what is the context, right? Because that's the application. So it's 30 what? There are 30 bees in the town at week 0. Okay? So we always kind of want to give that information out. Now, if this, and this is definitely a question or a test, a type of question that would be given where you can use your calculator, what I'm going to do is I'm going to go to my graphing calculator and I want to enter this in. So I want to show you a couple things really quick that we haven't talked about yet. We're going to do a lot more of. But grab your calculator and we want to type in the function itself. Let me see if this works the way I want it to. There we go. So here's a little hint, and this works if you have a TI-84 calculator. So I've got an option. If I hit y equals, I don't know if you know this, I just learned it a couple years ago. If I do alpha y equals, I end up with the first option that pops up, which gives me a fraction. And I think that's really helpful to know. So I'm going to type in, and I know it's kind of hard to see this probably, but I'm going to type in the function. If you don't have the option of putting it as a fraction, then you have to just put parentheses around this whole thing and use the divide, and I'll show you that in a second. But what I want to do, oh no. Okay, we might have to scratch this for today. My calculator, I have a free TI-84 Smart View app that I downloaded, and it froze up, which is not cool because I can't show you what we're going to do here. So, well, let's take a look at another option. Desmos is always, I was going to do Desmos, but it doesn't do the same thing I want it to. So if you have your graphing calculator, you could just type this in. This is not going to work the way I want it to today. So let's just use this information the way it is, or for what we have right now. So then part B says, how many bees are in the town after 1 week? So this case, all I have to do is plug 1 in, but I just want you to look at this graph really quick. This graph here is an exponential graph. It's growing very quickly, and you can see that. Why is it exponential? Because we have a base e. And if I plug in 0, notice that's the same answer we got. The initial amount was 0. But what is it after 1? Well, this is hard. I'm not guaranteed to get exact. Oh, hey, there we go. I was able to scroll on Desmos to find 1. Or I could just type in t equals 1. Actually, I think they want x in this case. If I type in x equals 1, that puts a vertical line at the spot 137.881. So this would be my answer to when t is 1, the population of 1 is 37.888, which if we're rounding it to bees, we would say 38 bees at week 1. Now, the whole reason why I wanted to do this problem was not those first two questions. What we're looking for is we're looking for the rate of change. And that's the second question here. What is the rate of change of the bee population at exactly 1 week? Include units. Well, I was planning on doing this with our calculator, but since I don't have that, or since that option doesn't work right now, we're going to try to do this by hand. And let's see if this works out. It should. Find the rate of change. Wait a minute. Rate of change. That means slope. Wait a minute. We want the slope exactly at week 1. I want the slope exactly at 1 point. That sounds more like a derivative. So what I need to figure out, so for part C, I have to find the derivative at time 1. Now there's two options here. I think this is kind of a cool thing. You could do quotient rule. You can do quotient rule right now and it'll work. Or what if I take this denominator and I write it out of the denominator and put it up top? And then that just means this is going to be a -1. So I can actually avoid the quotient rule and do a chain rule. This is only possible because of the constant up top. If this had a t value here, then I could rewrite it and I'd have to do the product rule. But since it's a constant, that 1200 is just a multiplier. So I can just do the chain rule now to find this derivative. All right, now notice the 1200, that's just a constant. But I have my outside function, which is something to the negative first power. And then I have my inside function, which has the e to the x in it. Okay, so if I do the derivative, the 1200 is going to stay. The negative 1 is going to come down in front and multiply, and then I'm going to take 1 away. So I get a negative 2. All right, so that's the derivative of the outside. Keep the inside. And then the chain rule part is the derivative of this inner piece. And we actually have a double chain rule because we've got an inside part on the e. So now I'm going to multiply by the derivative of this inner piece. Well, the derivative of 1 is 0. 39 is just a multiplier, so that's going to stay. And the derivative of e to anything is itself. But then we have that extra chain rule because I now have to take the derivative of the inside part, which is negative 0.24t. So this does not look super friendly, but all it is just either a quotient rule or a chain rule if you rewrite it. And it doesn't matter, you get the same answer either way, it just might look different. Well, now I could simplify this, but to be honest, why? I'm just going to figure out what is the rate of change exactly at week 1. Well, I'm going to come over here, and anywhere there's a t, I'm going to plug 1 in, and then we're going to just use our calculator and get an answer. All right, so I'm going to do some simplifying here as I write it. This will be negative 1200. And I know that if I plug a 1 in here for t, I'll just get negative 0.24. And same thing here. If I plug in, oh, that should be a negative 2. If I plug in a t being 1 here, that will give me a negative 0.24. And if I plug in a t being 1 here, I don't have to actually physically show that I plugged in 1. And then just grab your calculator, and you can type all that in if you use parentheses correctly. I'll do that quick. Okay. So when I typed in all of this into my calculator, hopefully I typed it in right. I didn't actually double check it. But what did I get? I got 8.804. Now, we're going to actually skip part D just because of the time here, but what does that mean? Well, we have to go back to what we're kind of looking at. We found the rate of change. So I found the change in the bee population. So I have 8.804 bees per week. Now, what does that mean? It's a positive number, right? My rate is positive, so that means that the population of bees is growing exactly at 8.804 bees per week, and we should be even more specific, at week 1, right? Because if I checked that at week 20, if I put 20 into the derivative, that number would be different, and most likely would be growing even faster. All right, now here's what I wanted to do, is I wanted to show you that at point 1, what did we just find? We found the slope of the tangent line. That's what the derivative is. But that derivative can help us discover how things change. All right, so we're going to do more on this. I have to find a way around of somehow showing you guys how to use your calculator more. And if my app is going to freeze every time I try to use it, I'll find a different route. It might be me holding my screen up like this and just showing you and going through it step by step. I don't like that method, but it might be the only route. Okay, so that is just using the derivative to answer problems. We've done that already. It's just a big focus, and we're going to do it for the next couple of weeks as well. All right, we are shifting gears here. You definitely want to write this down here. So we talked about 4.1. That was just using the derivative to answer problems. We call it the application of the derivative. Yesterday, you were supposed to just watch a video and take some notes. And that was section 4.2, which was called linear approximation. And all that was just writing equations of tangent lines and then using them to estimate a point without a calculator. And hopefully the video gave you guys the idea that the approximation, the equation of the tangent line can be used to approximate a value from the original function. And a lot of times that linear equation that we wrote, the equation of the tangent line, is easier to use than the original equation, and it's going to give us an answer that's close to the same answer. All right, so those were, and you think, why are we doing this? Can't we just plug it into our calculator? Yeah, but think about long ago when you didn't have a calculator, right? When the people didn't have a calculator, that's how they had to find the values of these really crazy functions, because they didn't have all the technologies that we have now. All right, well, today we're making a shift, and we're going to actually explore limits again, which is why we did the warm-up that we did. In section 4.4, we're going to spend 2 days on this. It's called L'Hopital's rule, and it looks kind of like a interesting name. There's this dude named L'Hopital. You could go look him up if you want. But basically, they discovered that whenever a limit has an outcome of 0 over 0 or infinity over infinity. Now we have to be careful. It's not equal to 0 over 0. It just means the top is going to 0 and the bottom is going to 0. Or it could be going to positive infinity or negative infinity. But what happens is when the numerator and the denominator approach a value that we don't know, we call that an indeterminate form. So in that case, if we reach an indeterminate form, L'Hopital's rule states then we can just take the limit of the derivatives of the numerator and the denominator instead. So instead of just applying the limit, we can take the derivative of them and it will give us the same value, which is kind of a cool, really nice approach. Right? I do want you to note, and by the way, this will make more sense when we do an example or two. But I do want you to note that we never ever say the limit is equal to 0 over 0 or infinity over infinity. You cannot say that. If you use the equal sign incorrectly, they're not going to give you the points on the AP test. And this is something that they most likely will include on a free response question, which means they're going to look for accurate work. It's not going to be a multiple choice question. All right. And then the other thing is, since we're going to be taking the derivative of the numerator and the derivative of the denominator, I do want you to know that all derivative rules, product, quotient, chains, powers, all of them that we learned still apply, which that's why calculus is challenging, is everything we learn, you still have to keep applying. All right. So we're going to look at, to be honest, the biggest thing you need to take away from today is proper notation. Okay? Please use proper notation. And we're going to look at those two limits that we had for the warm-ups. And I'm going to show you how L'Hopital's rule could be applied to this. All right. So I don't want to show a ton of work here. So I'm not going to write out step 1, do this, step 2, do this, because it's kind of the same. But please pay special attention to how we're going to do this. What I need to check is I need to check the limit of the numerator. By itself. So notice, I didn't put equals here. I just drew a line, and I'm just saying we're going to check the limit of the numerator. Well, that is substitution. So if I plug in 2, I get 2 squared minus 4, which is 0. So the numerator goes to 0. Then I'm going to check the denominator. And all we're going to do is do substitution. I'll plug in 2. And notice the denominator goes to 0. So now I'm going to compare. Notice I didn't say that the original limit equals 0 over 0. That's what we're saying. Never ever say this limit equals 0 over 0. This is our indeterminate form. Why do we say it's indeterminate? Because we cannot determine which function is going to 0 faster and which we don't know. We know that both limits are approaching 0, but a limit isn't an answer. A limit is what we're approaching. So we don't know what the outcome is. Okay, now, we didn't technically do L'Hopital's rule yet, but what I did was I showed that I reached the indeterminate form. You have to show that you reach the indeterminate form first. Okay? So now that I have shown that, I usually do this. I put a frowny face because that doesn't give me an answer, right? I don't like that. So then I draw an arrow from the original problem, and I'm going to apply L'Hopital's rule. Okay? Now notice, I actually indicated that I use L'Hopital's rule. You don't have to write the words L'Hopital's if you have the 0 over 0, because that's our sign. If you see the indeterminate form, apply L'Hopital's rule. Well, what is L'Hopital's rule? It says take the derivative of the top over the derivative of the bottom. So right now, these are just really friendly. We're going to take the derivative of x squared minus 4, which is just 2x. And then I'm going to take the derivative of the bottom, which is 1. And notice, by taking the derivative, that actually reduces out this 0 over 0. And now, notice how I'm confidently putting an equal sign. Now I'm just going to do direct substitution, and I can use my equal sign. All right, so my answer is 4, and that is exactly what we got in the warm-up. L'Hopital's rule is super friendly and actually quite easy once you get the hang of it. The hardest part is showing the correct notation, and that's what today's all about. All right, so let's look at the second one. And I will admit, these are much easier problems right now than you're going to see on an AP test. I just want you to get the structure, and then we'll start building on the more challenging problems. So, what if I take the limit of the numerator? Okay, now notice, this is the limit as x goes to infinity. So you do have to show this work. Everything that I'm showing almost the bare minimum here. Okay, so you got to show the limit of the numerator. The step you can skip is actually plugging in negative infinity, or plugging in infinity. You can skip this work right here and just say the answer to the top limit is negative infinity. And notice, no equal signs here from the original limit. I'm just showing that I'm checking each limit. Now here's what I mean by not showing work, or you can skip. If I plug infinity in here and infinity in here, I don't need to show that work. I know that infinity to the fourth power is positive infinity, and I know that infinity times 2 is infinity when I add them together. I know those are going to be infinity, so you can skip that work. But what do I have? Then I have to show that I compare, and I'm not using the equal sign. I'm just going to say, what is the top limit compared to the bottom limit? Well, we don't know. These infinities are not the same, right? They're not going to infinity at the same rate. So there's my indeterminate form. Excuse me. So you have to show this part right here. I need to see that part. Okay, now that is my signal for applying L'Hopital's rule. And what is L'Hopital's rule? All it is take the derivative of the top over the derivative of the bottom and apply the same limit that we were given before. So the derivative of negative 3x is negative 3. The derivative of 4x, or excuse me, x to the fourth is 4x to the third. And then the derivative of the 2x is just 2. Notice, by taking the derivative of polynomials, you're reducing out a degree of x each time. Now, sometimes we have to keep doing it. By the way, you can use L'Hopital's rule as many times as you want. So if this answer didn't give us a form that we knew, if it gave us another indeterminate, then I would have to do L'Hopital's rule again. And you just keep going, taking the derivative until it's done. But notice what happens here. If I plug in infinity here, I might show this work just so you guys can see it. What happens? I get infinity cubed times 4 plus 2. That whole thing is going to be infinity on the bottom. And anytime I have a number over infinity, that's going to 0. And there's the same answer we got, but by doing the end behavior model. We got the end behavior model in the warm-up. L'Hopital's rule got us to the same answer. So hopefully that's just a little bit of evidence that L'Hopital's rule works. All right.
Wait, so we can take like the negative infinity and compare it to a positive infinity?
Yeah, it's the same as
Like that, okay?
yeah, it's the same as like if I had the number 3/4. Notice how it's just a -3/4. The negative
Mm-hmm.
is just a really big number. Now, we have to be careful because this answer, we don't know. I'm not using the sign to determine the answer. I'm using the fact that the top went to infinity, negative infinity, and the bottom went to infinity, which means this is an indeterminate form. So I can't use just substitution to solve it. I have to take the derivative. Okay. Um,
Oh,
all right. So a lot of people have this question right here. How does this turn into zero? And here's the way I like to think of it. Now, let's say just separately, let's think of a different problem here. And it'll work better if I have this. Let's say I have a 10-foot long rope, right? So I have 10 feet of rope, and I want to divide that into an infinite amount of pieces. I cut the rope that's 10 feet long into an infinite amount of pieces. How big is each piece? It's basically so small that you can't even see it, so it's going to zero. And that's what happened. When you have a number up top divided by infinity, infinity is so big that it makes this fraction really, really, really small. It's like having one, or let's say it's like having -3 divided by that, right? That's so small. That's not even close to infinity, right? But this is going to be such a small number that we're going to say eventually it heads to zero. So we're going to, I think I have it on the next slide actually. We're going to just confirm a couple of things that is really good for you guys to know. So I don't know if you want to write this down, but it's things to think of. So what happens when I have a number? What happens when I have a number divided by zero? Well, you can never divide by zero. It's one of the 10 commandments of math, right? Thou shalt not divide by zero. That is an undefined function. But what happens when I have zero divided by a number, right? Well, zero divided by a number is just zero. And then what happens when I have a number divided by infinity? It doesn't matter the number, but if I divide something into an infinite amount of pieces, that's equal to zero. What happens if I have infinity divided by a number? What if I have a rope that's an infinite amount of length and I cut it into 3 pieces? Well, if it's an infinite amount, that amount is still going to be infinity. So these are just important concepts to understand that kids often kind of forget about. Other ones that are important for us to understand, and just a quick refresher, we've talked about these before, is thinking about this graph of e to the x, right? So what is e to the 0? Well, I didn't draw this perfectly, but anything to the 0 power is 1. Anything to the first power is itself. But what about e to infinity? What happens as I go to the far, far right of this graph? Where is my function headed? It's heading up as an output of infinity. But it's the next one that's important. There's 2 ways to think of this right here. We don't like that negative. So I'm going to flip this upside down and call it, because of the negative, e to the negative infinity, it's 1 over e to the infinity, which, wait a minute, isn't e to the infinity infinity? And isn't 1 over infinity equal to 0? If I have a rope that's 1 foot long and I cut it into an infinite amount of pieces, I get 0. So you can think of it graphically, or you can use your properties of exponents to rewrite this part. But these are all important things to remember to do without a calculator, because they're going to come up. And then we have the same thing with the natural log. We've already talked about this one as well. I just want to make sure that everyone is kind of on the same page with this. My graphs that I'm drawing are not great, but you don't need a great graph to understand this. So the natural log of 0, when x is equal to 0, there is an asymptote at x equals 0, which means the natural log of 0 does not exist. The natural log of 1 is 0. The natural log of infinity, what happens as I go to the far, far right, this graph is slowly increasing, but it will eventually keep going up and up and up and up and up. So that'll go to positive infinity. This one won't happen often, but what if I go to the far, far left? There are no outputs. This is actually not in the domain of the natural log of x, so this does not exist as well. So those are just things that we expect you to know. And I'm a visual learner, so if I ever forget one of them, I just result back to the fact that I know what the graph looks like for both of these, and then I can figure out the answer. All right, so now these pieces are going to come into play, especially when we start taking the limit of a top or a bottom, and we apply L'Hopital's rule. All right, so let's start looking at some ones that we've actually done these exact same limits before. And again, these are some simpler pieces just so you guys can start building your confidence. They will get harder. All right, so what do we have? The limit as x goes to 0 of sine of 2x over x. Now again, your goal here is to show the appropriate amount of work to get full credit. Don't skip steps. In my mind, this is one of the easiest things to earn points on the AP test if you just follow the expectations. So what do I got? I've got the limit of the top as x goes to 0. So I want to compare that separately to the limit of the bottom. I'm not putting equal signs. Now, if you know this answer, then you got it, right? What do we got? The limit as x goes to 0, I can just plug in 0 right here, and 2 times 0 is still 0. So then I have to think of what is the sine of 0, right? And that's where I'm going to just do this really quick. If I go over 0, this is kind of a unit circle. I'm at the spot 1, 0. Cosine is the first one, sine is the second one. So the top limit goes to 0. The bottom limit, if I just plug in 0, there's no work to show. So now I want to compare. I'm not putting equal sign. I'm just saying that that's an indeterminate. Right? There's our proof that just evaluating the limit does not result in an answer. So L'Hopital's rule is going to be applied. And hopefully you're going to see why we only do this once. The derivative of the bottom is 1. The derivative of the top is a chain rule. I've got the derivative of sine, which is cosine. Keep the inside. But then the chain rule is the derivative of the innermost part, which is 2. All right, now you can see, and this is why I'm going to use an equal sign. I know the bottom is going to be 1, so I don't have to plug in 0 here. I know I'm not going to get an indeterminate form. So I'm going to get cosine of 2 times 0 times 2. Well, this is just 0, and what is the cosine of 0? It's 1. We already discovered that. So this becomes 1 times 2 over 1, which is 2. So notice equal signs when I know I'm going to get my answer. By the way, we also knew this answer from a graphical interpretation. We knew the sine of x over x as x went to 0 was 1, and the 2 just doubles it. So there's more confirmation that L'Hopital's rule works. Okay. I don't want you to, maybe I do want you to write this one. This one you often see on AP tests. Natural log of x is very important for us to think of. So I'm going to go a little fast on this one though. So what are we going to do? We're going to take the limit of the numerator, which we just talked about this one. You don't even have to plug in infinity. You know the natural log of infinity is just going to go to infinity. That's all you need to show right there. And then on the bottom, you do have to show that you're taking the limit of this. So you have to write this limit out, which I know kids are like, well, I know that if I plug in infinity, it's going to go to infinity. So get over the fact that we have to do some extra work. But now when I compare, I'm not putting equal, I'm just saying that that results in the indeterminate form. All right, so that work, this is the work that allows us to say, we're now going to do L'Hopital's rule. All right, now here's the tricky piece. I'm going to try to do some no. So somebody, I just saw a chat here. Somebody asked if I stop writing the 1 here, will you get points off? No. If you don't put the 1, that's fine. It's always implied that there's a 1 there. However, if it canceled out from the top, you have to write it in the numerator if there was just a 1 there, because that changes the meaning. But notice here, watch how I write this. Well, actually, maybe I'll do this. If I take the derivative of the top, that's just 1 over x, right? And then the derivative of the bottom is 1. Now, there's 2 ways to kind of think of this. If I have 1 over x divided by 1, that's the same thing. That's the same thing as writing it this way. 1 over x, and I'm trying to match my colors here, times by 1. Now notice we don't have to write the times by 1 over there. But now I'm confident in the fact that if I put in infinity, I can put equal signs here because I know that this is going to actually result in a rope that is 1 foot long divided into an infinite amount of pieces ends up being 0. All right, so my hopes are you're now confident in the work that you have to show and the act of taking the derivative over the top over the bottom. The only thing that makes this more challenging is the types of functions. The work is exactly the same, but every once in a while we get we have to do L'Hopital's rule another time, and sometimes we have to do it 2, 3, 4, 5 times. And that's what the goal of the next couple of problems are. So I want to just double check this quick. I think I want to do this one for sure, because this is kind of what your homework's going to look like. Notice the problem is a lot more confusing. Okay? It doesn't work as well, or in terms of it just isn't as nice. So our goal is to evaluate the limit and write your answer in simplest form. Well, the first thing I'm going to do is just show the work from the top. And I realize we're kind of short on time here, We got 14 minutes, but definitely want to see if I can get through this part. So we got the top limit, and we're just going to evaluate it by plugging in 0. Now notice e to the negative 0, well, 0 isn't really positive or negative, so this is just e to the 0, which is 1. 1 minus 1 is 0. So there's my numerator limit. The denominator limit just has extra pieces in it. And I know the annoying part is right here. Kids always skip this step. But you have to show that you're taking the denominator separately, right? After that, if you can do the rest of this in your head and just write the answer, you're fine. I don't like to do that. I like to plug in 0. And then notice, we do know that the sign of 0 is 0. So I get 0 times 3 plus 0. You don't need to show all that algebra. You can just say, okay, I had shown that I get 0 over 0. Right? So I basically have shown that I'm allowed to do L'Hopital's rule. And what becomes tricky now is the same stuff we just tested on. Can you take the derivative of the top? Well, notice we have a chain rule here. And that's the part that makes this tricky. So deal with the outside first. So if I have e to the negative x, the derivative of e to the negative x is itself. And then I have to multiply by the chain rule. And the derivative of the inner part is negative 1. And I might just write the word chain here so we don't forget. And the derivative of the minus 1, that's going to be 0. So here's the derivative of the top. And if you really get good at this, you could just write the negative out here instead of putting it there, but that's the route I'm going to take. All right, now the bottom. We have another chain rule. See the inside right here? I've got a negative x. So the 3 is a constant. It's going to stay. The derivative of sine is cosine. And then we're going to keep the inside. But then I have to multiply by the derivative of this inside, which is negative 1. So that's the chain. Then I actually have this extra little plus 3 at the end, so I got to put a 3 here. The derivative of 3x is 3. Now this is the part where I'm not certain yet. Okay, and I don't remember if this is going to help me out or if it's going to hurt me. So here's what I'm going to do. I'm going to evaluate as if I think that this answer is going to be an indeterminate form. So I'm going to plug in I'm going to evaluate just like we did up here, the derivative of the top. We're going to plug in 0 and evaluate that limit. Well, e to the negative 0 is 1, so I actually get negative 1 up top. All right, that's a good sign. That means that I most likely won't be an indeterminate form, but it doesn't mean my answer is guaranteed to exist. So now I'm going to do the limit of the bottom. And you could take this negative 1 and make that a negative. I think I'm going to do that for this next step. So now I have my limit of the denominator. I'm going to plug in 0. And I want this negative 1 to multiply the beginning 3. And then I have cosine of negative 0, which is something that we know. We just saw that. The cosine of 0 is negative 1. And then I end up with negative 3 times negative 1 plus 3, which ends up being 6. Well, when I compare those, I get negative 1 over 6, and that actually is an answer that I'm happy with. So I could have been successful in just plugging 0, but I wasn't sure. So I'm just being safe. The trickiest thing is just remembering the chain rules. That's usually where students make mistakes, and that's what they test on the AP test. So they're looking to make sure you remember the chain rule. All right, let me see which one is better. How about this? I don't want you to do this problem. I just want to show it to you so you guys can see it. So I'm going to go really fast. What I'm going to do is check the limit of the top. So if I just plug in infinity, we know the natural log of infinity is infinity, right? So there's the top. And then on the bottom, I've got 2 times the square root of infinity. Oops, this should be an x. So if I just plug in infinity, the square root of infinity is still infinity. So I end up with that indeterminate form when I compare. I don't like that, right? Infinity over infinity doesn't tell me an answer. So I'm going to do L'Hopital's rule. And I can pretty confidently take the derivative of the top. Now watch how I do this and see if you guys agree. The derivative of ln of x is 1 over x. Well, instead of writing it like this, 1 over x, the 1 is in the numerator and the x is in the denominator. Right? So that's going to kind of push things back into the denominator. And then down here, the derivative of this, I might treat this as side work. Right? I might come over here and say, okay, wait a minute. If I want to take, my function is y equals 2 to the square root of x, I can rewrite the square root of x as a 1/2. And then when I take the derivative of it, the 1/2 comes down and multiplies by the 2, and then I take 1 away. Well, in that case, the 2 and 1/2 go away, and I'm left with x to the negative 1/2, which is the same as x to the square, x over 1 over the square root of x. So notice how the derivative of the top actually kind of pushed into the bottom. And notice how the derivative of the bottom is just a, actually, I gotta be really careful. The derivative of the bottom is 1 over the square root of x. Now, what happens here? If I plug infinity in the top, I end up with the limit as x goes to infinity of 1. Well, that's always going to be 1. So my top is going to stay 1. But what's the bottom going to do? I could try to simplify this out, but to be honest, you don't really need to. What happens here is I end up with infinity times 1 over the square root of infinity, which actually ends up being 0, right? Oops. 1 over the square root of infinity is the same as 1 over infinity, which that's really infinity times 0. Now, this is the part that I don't like. It's a little bit weird. This was an odd one. So just to be safe, I might try something a little different here. What if I have the x on top over the square root of x? Wait a minute. Algebraically, that's the same as x to the first over x to the 1/2. And if I reduce that down, this algebraically ends up being x to the 1/2. So it's like the square root. So that tells a little bit different story. So I know the top would remain 1 and the bottom would remain the square root of x. So now I can just plug in infinity, and that actually proves that this limit will go to 0 as the algebraic simplification. So sometimes you can see that if you don't simplify, it produces a result that isn't really cool. It still works because this technically is 0, but sometimes simplifying algebraically is more help. Now notice I didn't take the derivative to go here, so I didn't use L'Hopital's rule. I just got an answer that was a little confusing, so I checked it algebraically. I think we're going to save this one for next week. So here's what we got. Your homework tonight is 6 problems in Delta Math. And I chose Delta Math so you can check their work. And you have 3 chances to do each problem. And I assigned specific ones. So if you don't get it right, make sure you're reading why you didn't do it correctly. And it's all about showing work. Don't forget about chain rule. And what I'm going to have you submit, instead of submitting a screenshot, you're going to submit your written out work to Schoology for this Delta Math problem. All right? So what if you didn't do well on the Chapter 3 test? Okay? You can do corrections on that. It is due by Sunday night. What you would do is you'd open the test. I have to do this. I'm going to do this as soon as we get done with our class, but I have not allowed you to see your answers yet. But I'm going to do that now in the next 25 minutes. So open the test, correct any problem that was not 100%. I did give some partial credit. That was my way to curve the test. Instead of getting something wrong, I looked at your answer and decided, based off of that answer choice, was it partial credit or not? And then I also looked at the work that you submitted. Anyways, anything you didn't get 100% correct, show your work. Be neat, clean, accurate, and then email me a photo when you're done, and this will boost your score up to a 75%. Okay, so here's what I got. We're done with class.